Students, welcome back. Today I'm going to review chapter 16 and 18. Chapter 16 is on acids and bases and chapter 17 oxidation reduction. So for acid bases we talked about pH, pOH indicators, a little bit about buffers and about acid-base reactions. That's transfer of protons. Chapter 18, oxidation reduction. Oxidation is losing an electron, reduction is gaining an electron. We talked about the reactions, oxidation, reduction, reaction, half reactions, and then balancing to the total reaction. Acid bases. For acid bases, we use the Bronsted-Lowry definition. An acid is a proton donor, protons H+, and a base is accepting this proton. And when we talk about acids and bases, they're always in water. So we have some acids and bases here. You see here HCl as an acid. The H+ is donated to H2O. H3O+ is formed. HCl and Cl-, they're together. We call it conjugate acid-base pair. We can do the same for a base. So O2- is the base here, accepting an H+ from H2O, and OH- is formed. More in general, when we have a base Ba accepting an H+ and is formed Hb+. The B and Hb+ are my conjugate base acid pair. They always go together. And of course, sometimes we have ionic compounds like sodium hydroxide. When we dissolve in water, we receive a basic solution because it contains a lot of OH-. And remember, when we talk about H3O+, it's the same as H+, because H+ plus H2O is H3O+. We talked about the strength of acids and bases. We have strong acids and weak acids, and as well strong and weak bases. Strong acid-base means they completely ionize in water. So I have the maximum amount of ions, so the maximum amount of H3O+ or OH-. And you see one reaction arrow. And when we have a weak acid or a weak base, they do not completely dissociate in water. And we have an equilibrium. So there's a reverse reaction. You can see the equilibrium sign. So when I have 1 mole per liter of a strong acid, it contains a lot more H3O+ than I have 1 mole per liter of a weak acid. Now pH, pOH. How do we assess the pOH and the pH? pH minus log H3O+ or minus log H+. When I know the pH, I can assess the concentration of H3O+ by the inverse of log, so 10 to the minus pH. I can do something similar for pOH. pOH is minus log concentration OH-. When I know my pOH, I can assess my concentration of OH- with OH- is 10 to the minus pOH. And that's something really important. pOH plus pH is 14. Why is that? Because we have the water constant. Concentration H3O+ times concentration OH- is 1 times 10 to the negative 14. So water is a little bit dissociated in OH- and H3O+. And when we have a pH of 7, the solution contains the same amount of H3O+ and OH-. So the one thing about significant figures and decimals, the number of significant figures in my concentration is the same as the number of decimals in my pH or pOH. So if I have a concentration of 1.0 times 10 to the negative 2, I have 2 significant figures in my concentration. That means I have 2 decimals in my pH. So when do we call a solution acidic? Well, it's when the pH is smaller than 7. And that means my concentration H3O+ is larger than my concentration OH-. pH larger than 7, we call it basic, and that means concentration OH- is larger than concentration H3O+. And when the pH is exactly 7, we call it neutral, and then the concentration H3O+ is the same as the concentration OH-, and that's 1.0 times 10 to the negative 7, because they form together the water constant. So strong acids, completely dissociation, we only know 7 of the strong acids. And strong bases, we also only know a few. A couple we can have these solutions of ionic compounds containing hydroxide ions. So strong acid, completed dissociation, and strong base, also completed dissociation. So when we know the concentration of my strong acid, I immediately know the concentration of A3O+. So I can plug it into my pH is minus log concentration. So if I have, for instance, 1.5 mole per liter HCl, then my pH is minus log 1.5 because completed dissociation of HCl into H plus and Cl minus, or A3O plus and Cl minus. Then we have the acid-base reactions. We're going to transfer H plus from an acid to a base. Well, overall, in the net ionic, it's H plus OH minus becoming H2O. And we also call it a neutralization reaction. You can see here HCl plus NaOH. H plus is going to react with OH minus, water is formed. Nitric acid, HNO3 with calcium hydroxide, this is my base. And here H plus from nitric acid is my acid, they form water. Then we talked about buffers. What is a buffer? It's a solution that has more or less a constant pH. It will hardly change when I add small amounts of acid or a base. How can we make a buffer? It's a weak acid and a weak base together. So I can never make a buffer with a strong acid or strong base. It should be weak acid, weak base. Next chapter, oxidation-reduction. Oxidation, losing electrons, reduction, gaining electrons. How can we remember that? Oil rig, oxidation is loss, reduction is gain. Or Leo the Lion says Ger, losing electrons, oxidation, gaining electrons, reductions. And for oxidation reductions, oxidation states or oxidation numbers will change. How do we assess those oxidation states? We had 7 different rules. You can see them on page 677 of the book, but the most important one are in red. If I just have an atom like calcium, sodium, iron, gold, 0. If I have monoatomic, like NaCl or whatever you have, magnesium oxide, we use the charge of the ions. And you can use the periodic table to find the charge. Remember, group 1 has +1, group 2 has +2. And then the two most important one are thing number 3 and 4. Oxygen almost every time has an oxidation number of -2. There are some exceptions. So I had the examples here. CO, O has oxidation -2, that means C has +2, because overall it's 0, and that's rule number 6. Neutral compound, total oxidation state is 0, and CO is neutral. CO2, also neutral. Now I have 2 oxygen, makes overall 2 times -2 is -4 for oxygen in total. So carbon must have +4. Another important one is H. In covalent compounds, so molecules or ions, we have an oxidation state of +1. If I have binary compounds like H2O or Na3, the element with a larger electronegativity gets the negative oxidation state, and that's equal to the charge of the anion. So have an example, Na3, well, H is always +1, so there must be N is -3. H2O is the same. And remember, large electronegativity is in the upper right corner of the periodic table. Fluoride is the atom with the largest electronegativity. Okay, so then we had the reactions. Well, we have proton transfer for acid-base reactions, for oxidation-reduction reactions, electrons are transferred. And because electrons are transferred, my oxidation numbers will change. So oxidation means it's losing electrons, so it's increasing the oxidation numbers. And reduction was gaining electrons, so there's decrease of oxidation numbers. So that's how you can see if a compound is reduced or oxidized. And how do we balance oxidation-reduction reactions? Well, we have using half reactions. So we have a half reaction for the oxidation, and we have a half reaction for the reduction. For the oxidation, it's losing electrons, so my electrons are on the right-hand side of my reaction arrow. Reduction means it's gaining electrons, so the electrons will be on the left-hand side of my reaction arrow. So a half reaction, they always contain electrons. And if I add them up, my total reaction never contain electrons. How am I going to do that? Balancing oxidation-reduction reactions. So first of all, I separate my reaction into a half reaction for oxidation and a half reaction for the reduction reaction. And then we're going to balance each half reaction, balance in terms of type and number of atoms, but also charge. When I've done that, I have my balanced half reaction for oxidation and half reaction for reduction. I'm going to add these up. And I'm add these up in a way that my number of electrons lost and gained in those half reactions are balanced out, because my overall reaction cannot have electrons. So there's one more final example here. Na plus CO2 become NaCl. How am I going to balance this? My oxidation is losing electrons, so it's Na becoming Na plus 1 electron. Reduction gaining, so Cl2 plus 2E minus becoming 2Cl minus ions. And I want to add these up. And you see I have 1 electrons in the oxidation half reaction and 2 electrons in my reduction half reaction. So I have to multiply the oxidation half reaction by 2 and times 1 for the reduction half reaction. And then add them up and have my final reaction. Okay, the final thing we talked about, the battery, one of the examples. One of the first batteries, the Daniell cell, it was a zinc and a copper cathode. And zinc is oxidized, it's producing the electrons. They go to the other cell with the copper cathode. And the electrons we can use, if we have a light or whatever, we can use the electrons. And we have a flow of electrons from zinc to copper. And guys, and that's it.